All right, folks, so let's get started. I just want to remind everyone, please read my facts page that I have on our Carmen modules, right? I've only posted about 6 links, and one of those is the facts page, and the other one is the link to the synchronous Zoom session. So this week in recitation, next week for you Monday folks, I'm forcing everyone to read the facts page and the syllabus, and you'll answer a small quiz where you'll go over the course logistics. So in short, if you don't feel well or you can't come to lecture, you don't have to email me asking for permission, right? One of the links that I posted is the Zoom lecture link. It is available to everybody. You don't have to wait for my permission. You should not wait for me to say, yes, it's okay for you to Zoom in on lecture. It's available to everybody. Got it? Good? Okay. All right, so we will be finishing chapter 1 today. I'll make sure of it. So we left off talking about scientific notation. So the big thing with scientific notation, it's the best way to convey the number of sig figs in a value, especially for a large number. So if we look through some of these, so the volume of gas used in the US every year. So this is the standard notation, so written as a big number. So what you should do is inspect that number and think, okay, how many significant figures is it trying to convey? So when I read, that 55,000,000 liters number, I see that there are 2 sig figs there. So I want to convey my scientific notation to two sig figs. And so that's what you see here, 5.5 times 10 to the 11 liters. So make sure you have that unit there. All right. And we can use scientific notation for small numbers as well. Same thought process. Look at the number, how many sig figs are written in that number, and make sure that you convey in scientific notation that same number. So for example, if we wanted to convey a head of an ant to 0, let's say we do 0.00060 meters. So this number written, how many significant figures are there? 2. Because there's a decimal in it, that last 0 counts. Because, I took the extra time to write that last 0, so we want that to count as a significant digit. So if we wanted to write that number in scientific notation, we would do 6.0 to convey 2 sig figs to the -4 meters. All right, and here's another small number again. So the diameter of a chickenpox virus. So here, we're given scientific notation. Let's go back and put it into normal notation within here. So here, there's 1 significant digit. So we want to make sure our standard notation also has 1 significant figure within it. So that's significant figures. Last class, there were some questions about addition, significant figure rule. So let's just kind of revisit that. All right, let's take the average of these 3 numbers. So recall what an average is. You take the sum of all the numbers, and then you divide by the number of values. So how many values are here? 4, right? So the number 4 in the denominator, how many significant figures are in the number 4? So we think it's 1, right, when we think about the number 4. But remember, significant figures, the reason we communicate them is to communicate certainty of our measurements. So the number 4, is that an estimation at all? No, it's actually an exact number. Would you bet $1 million that there are 4 measurements there? Yes, so it actually has an infinite number of sig figs. It's not 4, it's really 4.0000000. All right, so keep that in mind. So in averages, the number of values will have an infinite number of sig figs. So we care more about the sum. That is where our significant digit information is going to come from. So when we take the sum of these 4 values, we're doing addition, subtraction. So recall the rules for addition, subtraction, right? We take these numbers, we add them. It's best to just put the numbers on top of one another like we're in grade school. So I'm going to do that. So 48.1, 50.2, 51.38, and then 49.6. So how addition subtraction works, and in this case we have 4 different numbers. You want to look for the rightmost common place all of the values have. And then that is where your last significant digit in your answer will be. So let's think about it. right? All the numbers have a significant digit in the tens place, right? So that means the answer will have a certainty in the tens place. They all have values in the ones place. They all have digits or certain digits in the tenths place. So our answer can actually only go out to the tenths place. So if we looky here, this one number goes out to the hundredths place, right? But see how none of the other numbers have significant digits in that place? You see that? So that means our answer, we don't have certainty in this last place. So our answer when we do this, all right, so 48.1 plus 50.2 plus 51.38 plus 49.6. All right, so I get 199.28. That means when I take the sum, the last significant digit will be the tenths place, right? So it's with addition and subtraction, you don't just count significant figures, right? We don't count them, we look at the place values. That in this case, the last place value is the tenths place. So if we rounded this number, we would have 199.3, right? And so our sum here would have 4 significant digits. But we're not done. We still have to do the division. Right? So we take this number and we divide it by 4. But we just said that how many sig figs does this sum have? 4. It has 4 sig figs. So how many sig figs when we do division, how many sig figs will be in our average, in our answer? 4, not 3. Not 3. So this is an example where we actually gained confidence in our answer. And so if we divide that by 4, we get the average is 49.82 grams. All right, that's like the average mass of an egg, like a chicken egg. Okay, all right, so that kind of goes over averages and sums. Again, go to the chapter 1 overview sheet for more information about, or more practice on addition, subtraction, and multiplication, division. Okay, so scientific notation in your calculator oftentimes will work with really big, really small numbers. So if you haven't already, take out your calculator now. So here we have a little bit of dimensional analysis. It says a single bacterium weighs 1 times 10 to the negative 16 grams. How many bacteria are in 1 microgram of sample? So there's a couple of conversion factors that we need to collect here. So in the question, it says 1 bacteria equals 1 times 10 to the negative 16 grams. That is one conversion factor or equality that we can use later. And the question is asking, okay, how many bacteria are in a microgram? So we're starting with 1 microgram, and we want to figure out how many bacteria are there. So I need something that can relate grams and micrograms. And that just comes to our prefix chart that you need to memorize and understand that microgram means times 10 to the 6, or times 10 to the 6 micrograms are in a gram. So with all of these conversion factors, we can get our answer. So let's start with this value, 1 microgram. And I want to convert that to grams, so I'm going to use this second conversion factor. So I'm going to put 1 times 10 to the 6 micrograms on the bottom, because that will cancel the microgram part, and I'll put 1 gram on top. So now I'm in the unit of grams, so if you see those units cancel. And now I can use that first conversion factor, grams to bacteria. So I can put 1 times 10 to the negative 16 grams on the bottom, and then 1 bacteria on the top. And so you can see those units cancel, and our answer will be in bacteria. So I want to make sure that everyone uses their calculator and can get the answer here, because we're using scientific notation. So in recitation 0, I walked you through using the exponential function on your calculator, the E button. All right, so the E button is right here. So I have it circled depending on what your calculator is. If you have one of the bigger ones, you have to press second and then the comma button. It's above the 7. That E essentially replaces the times 10 to the. So for example, if you wanted to put 1 times 10 to the negative 16 into your calculator, you would put 1e negative 16, and it means the exact same thing. So it's really important that you practice this, because when you're at the exam, you don't want to be spending time trying to figure out how to put an exponential into your calculator. So it's best to learn this now. So how I would put this into my calculator, I would do 1 times 1 divided by 1e6, so that's that part. And then I would do times, oh my gosh. No, I wouldn't do times. I would do divided by 1e negative 16, and then press equals. That's what I would put in my calculator, so let's do that. 1 divided by 1e, okay. 1e, what is it, 6? 6 divided by 1e negative 16. And make sure you're using the negative button, not the minus sign for the negative. That's a common mistake. So the negative, oops. Oh no, where am I? The negative, so I had a student in my office hours and they kept getting errors. And it's because they were using the negative, the minus sign instead of the negative. So the negative sign's right here on the calculator. See, right there. Okay, and my answer I got is 1 times 10 to the 10. Did we get that? I hope so. So if you're not using exponential, the E button correctly, oftentimes it's because you're off by a factor of 10. So just keep trying and make sure that you get that. So what's the unit here? Times 10, 1 times 10 to the 10. What's the unit? Bacteria. So that's how much bacteria are in a microgram. That's a lot. All right, so that's using your calculator. All right, so we're, with dimensional analysis, we're oftentimes using units. So I have to talk about SI units. These are the standard units that all chemists and scientists relate to. These are the SI units. Oftentimes we don't use SI units in, so SI means standard units. We don't use them in lab because oftentimes they're just not useful, like a kilogram. That's really big. We never use a kilogram worth of material in lab. It's usually a gram. So just recognize that these units exist, but you'll oftentimes, in hospitals, in other sciences, you might use different units, but related to SI units, but not necessarily these SI units specifically. These ones, electrical current and luminous intensity, we'll never use these. So that's why they're like grayed out, right? But these ones are, you will run into often, kilogram, meter, second, Kelvin. We will talk about those types of measurements often, and you will take them in lab. All right, so let's talk about some of those units. So mass is just the measure of quantity of matter that we have. So like I said, a kilogram, that's the SI unit that scientists compare and reference to, but a kilogram is huge. We never use that much in lab. We're way, way more likely to use a gram's worth of substances. Unless you're like actually, in a chemical manufacturing plant, you will never work with a kilogram of substance at a time. So often we think about a gram's worth of substance. This is much more easier to work with in lab. So this is a gram of cocaine. That's a kilogram of cocaine. It's really big. So there's like a dime. So it's huge. All right. We don't work with this much. And drugs are bad. So oftentimes we use the terms mass and weight interchangeably, but recognize that there is a difference. Weight is the force that an object has based upon gravity. And so on Earth, we have essentially the same gravity everywhere. So mass and weight on Earth are somewhat the same. And chemists and just people in general use the terms mass and weight interchangeably. And that's because we all live on Earth and mass and weight are similar. But if you think about, when the astronauts went to the moon, right? And they were like bouncing on the moon. People will say, oh, they feel weightlessness, right? Because on the moon, there's less gravity. But the question is, when Lance Armstrong went to the moon, did he lose the amount of matter of his body when he went to the moon? No. So on the moon, Lance Armstrong has the same amount of mass as he does on Earth, but his weight is different, and that's because gravity is different on those two, like on Earth versus the moon. So there is a difference there, but generally when we're just talking about earthly things and you interchange the words mass and weight, most people will still understand what what you mean. Yeah, so weight does not equal mass except on Earth. Except on Earth, okay? So how we measure mass is with balances. So I think this like old school balance kind of really shows you that balances, when we measure mass, measures the amount of matter in your body, because these old school balances, right, those slides, that slide is you're literally moving a piece of matter to counterbalance how much you weigh. So you're comparing your amount of mass to a standard mass. And so you can clearly see that is measuring mass. But in lab, you know, these slidey scales are kind of hard to work with. So we use balances that have that are digitized and calibrated to a certain standard. So it's much easier to work with just readouts. So there's two kinds of balances that you'll work with: these top loaders that go out to 2 decimal places, and then these analytical balances that go out to 4 decimal places. And I already mentioned, how much does the top loader cost? It's like $400. And then the analytical balance is like $2,000, right? So it costs, 5 times as much for just 2 more decimal places. And those 2 extra decimal places, we have to actually change, how the balance is operated. We need this kind of like shield around where you make the measurement, because even a slight gust of wind would change the measurement. You'll see a change in that last decimal place within there. All right, so there we go. All right, so that's mass. Volume we also talk about. So oftentimes we will use volume measurements in liters. All right, a liter is pretty big though. If you think about like a 2-liter bottle, that's a lot of liquid. So oftentimes in lab, you'll be working with milliliters, all right? And so milli is one of our prefixes. And so I like to just memorize that there are 1,000 milliliters in 1 liter. All right, so keep that in mind. So that's, again, a prefix that you will often need to make that relationship between milliliters and liters. And I will point out, there is another type of volume unit that we use, and that is a cubic volume. All right, if you think about a cube, right? So it has like a length on this side, and a depth. All right, that's another way we can compare, think about volume like a cubic meter or like a cubic foot. So liters is a type of volume. A cubic meter is also a type of volume. So length times length times length. So volume can also be expressed like this. And I will just, the way you can kind of make the relationship between the cubic realm and the liter realm is this conversion factor, that 1 cubic centimeter is equal to 1 milliliter. That will help you make the relationship between those realms. All right. So for example, if we were talking about like a liter, 1 liter of soda is equal to 1,000 milliliters. So that is also equal to 1,000 centimeters cubed. All right, so all of those are equal to one another. So if you have a unit in milliliters, it's also the same volume in centimeters cubed. So that's how you can go between those 2 realms. All right, so we talked about mass and volume. What about, we put them together. All right, if we put mass and volume together for one certain sample, we can think about the density of a sample. And this is really useful to us because we can use density to identify objects. All right, so if you have one sample, you take its mass, you take its volume, look at the ratio between mass and volume, you get density. So water has a density of 1 gram per milliliter. So a milliliter of water, 1 milliliter of water will equal 1 gram of mass, and that's based upon its unit, right, when we think about dimensional analysis and derived units like this. So things that have less density, so like a piece of wood, will float on water. Things that are more dense than water, than 1 gram per milliliter, will sink in water. And so density is really nice for identifying substances, because it doesn't matter how much of the stuff you have, density will never change. It's only based upon the identity of the thing. Water, regardless if you have a cup of water or you're talking about the whole ocean, water will always have the density of 1 gram per milliliter. So that's really nice. So that is called an intensive property. That it's a property that is just based upon the identity of the thing. Intensive properties help us identify things. Other types of intensive properties or properties that don't change based upon the amount of stuff you have is like color, right? If you have a sliver of gold and a block of gold, color doesn't change. Contrast this to extensive properties. Extensive properties are measurements or observations you can make that do change based upon how much stuff you have. So mass and volume are the two big things that are extensive properties, that those measurements will differ based upon your sample. But intensive properties help us identify stuff. So like color, smell, density that we just talked about. We'll also talk about specific heat in a later, and temperature also is an intensive property. It doesn't really matter how much stuff you have. Okay, yeah, so intensive properties we use to identify substances. So here's just a list of common densities of substances. So we have solids, liquids, gases. So the general trend that you see, and I think that we can kind of relate this to everyday life, is that solids tend to sink in water, right? So liquids have this kind of medium density, and that's what you see here on this list. Solids tend to have higher densities. So solids are typically more dense than liquids, typically, all right? So liquids here are less dense. There are some exceptions, okay? And then gases would be the least dense of them all. Least dense of them all. You might be looking at these numbers and wondering why. So the unit here for gas density, it's not grams per milliliter, it's grams per liter instead. So we actually, that you have to kind of like take a big balloon of a whole liter in order to take a mass measurement of a gas, just because there's not a lot of matter in gases, and that's a good thing. We don't want our atmosphere to be super thick and soupy. We want our atmosphere to be nice and clean. And so, yeah, that's what you see, that solids are the most dense, gases are the least dense. And we can kind of think about that in terms of particles, right? And I think, do I talk about that? Not yet. When we think about the particulate level of solids, liquids, and gases. All right, so let's put it all together. All right, this is something that you'll do in lab, right? And that's taking a density of an object. So we have an object here. We bought a gold ring from a flea market, and we want to prove to our friend that it is in fact pure gold. So we want to calculate the density of this ring. So density is mass over volume. So let's look at the values that are given here. So density, mass over volume, I gave you the mass of the ring, so 16.98. So that value we have. Now we need to figure out the volume of gold that we have. So what's a little weird here is that I don't just give you the volume of gold, I give you a water displacement measurement instead. So I have a container of water at a certain initial water volume. Once I put that ring into the water, that ring will displace some of the water to a higher level. So that's kind of the picture that I drew here, that our water is initially at 8.65, and then once I throw the gold ring in, it increases to 9.52. So the difference here, the difference between these two values will be the volume of the gold ring. Do we see that? All right, so this is subtraction. So we're going to do subtraction. So 9.52 milliliters minus 8.65 milliliters. Okay, we'll do that math. So just based upon this, it's subtraction. To what place value will my answer go out to? The hundredths, or the second decimal place, because both values are known to the second decimal place. Okay, it's not so much, a number of sig figs, so let's actually do the subtraction here. So 9.52 minus 8.65. All right, so my answer is 0.87 milliliters. That's the volume of the gold that I have. Okay, so note here that, both of the volumes we started with were 3 sig figs, but our answer is 2 sig figs. But remember, that's okay, because in addition subtraction, you never count the number of sig figs. You look at the place values involved in the calculation. So in this case, because both of those volume measurements go out to the second decimal place, our answer must go out to the second decimal place. You see that? Yes. So just in your mind, you separate addition, subtraction over here, multiplication, division over there. Okay. All right, so that is the volume of our gold. That's the value that's going to go in our denominator. All right. So let's put that together. So mass of our gold is 16.98 grams over 0.87 milliliters. That's just what we got. So if we note here, if we look at sig figs, this top value has 4 sig figs. This bottom one has 2. So our answer will have how many sig figs? 2 sig figs. And so if you put this in your calculator, it's like 19 point something. 19.51 grams per milliliter, or we can say 19.51 grams per centimeter cubed. Same thing. If we round to 2 sig figs, it's going to be 20. 20 with 2 sig figs. So there is our volume of our mysterious ring. So let's ask ourselves, is it real gold? How would we know? We just got a density answer. How could we figure out if it was real gold? Compare it to the real density of gold. All right, so you can either look it up, Google it, or you just go up a slide and look right there. So do we think it's real gold? Yeah, it's pretty close to 19, so yeah. Because if it was fake, it would probably be like closer to copper, right? Or some other metal, so it would probably be less dense. So this is probably real gold, so that's cool. All right, so that's sig figs and thinking about identifying substances. Okay, so related to density and often used in health is specific gravity. So if you go to the doctors and they make you pee in a cup, they will tell you the specific gravity of your urine, because that can tell us a little bit whether we're overhydrated or dehydrated. So specific gravity, it's a measure of density. But it's special because it's a measure of density that we compare to water. Do we recall what the density of water is? 1 gram per milliliter. So specific gravity is just a ratio. All right, specific gravity, it's just the density of the liquid that you're inspecting, so your urine, over the density of water. So if you have a specific gravity that's more than 1, then you have then your thing that you're measuring, your urine, is more dense than water. If it's less than 1, then it is less dense than water. So typically when we think about specific gravity in urine, normal urine will have a specific gravity around 1.002 to 1.03. So that's like a healthy range for an individual. If your urine is more dense than the top range, so if we're like above 1.03 of a specific gravity for your urine, that means your urine is more dense. Okay. If your urine is more dense, you can think of there's just more stuff dissolved in your urine. Sorry, I keep saying urine. But this is important. Our bodies and health are important, right? So if there's more stuff dissolved in your urine that you're excreting, would you think you're dehydrated or overhydrated? Dehydrated. You're not drinking enough water, so essentially your body is trying to excrete a bunch of salts out. All right, so when you have really heavy, really dense urine, it means that you're dehydrated. And I think as humans, we kind of recognize that sometimes when our pee comes out really yellow or like really dark, we're like, ooh, I need to drink water, at least as an adult. When I was a kid, I don't remember drinking water at all. And now that I'm an adult, I turned 30 this year. I turned 30 this year, and I have to meter my water intake much more closely. I know I can tell when I'm dehydrated. All right, and so if we're less than this range, if we are less than 1.002, then we are overhydrated, which I would think rarely happens in people. It's more likely that we're dehydrated. Okay, so if we're overhydrated, there's much more water, there's less salts being excreted out, all right? So your urine will be less dense in that case, okay? All right, so let's think about temperature. We already said that temperature is an intensive property. It doesn't really matter how big your sample is. If your sample is a uniform temperature, it will have that temperature. All right, so really temperature is a measure of kinetic energy of your sample, how fast your atoms are moving. So if you have a solid and you're taking the temperature, we're looking at how atoms are vibrating in your sample. The more they're vibrating, the higher the temperature that you will record there. So what's useful to us as scientists and health professionals is converting between Fahrenheit, Celsius temperatures, okay? As you know, we live in America right now, and we typically think about temperatures in Fahrenheit. Okay? But in sciences, especially in calculations, oftentimes we need to convert those to Celsius or even Kelvin. So we need to know these conversions within here. All right, so here are the conversions to go between Kelvin and Celsius temperatures. So they're kind of directly related, that it's your Kelvin temperature is just plus 273 of your Celsius temperature. But Celsius and Fahrenheit, we have to do some division here because the scaling is a little bit different. So practice using these equations to convert between temperatures. So let's just do one practice one right here. All right, so hypothermia occurs at body temperatures that fall below 95 degrees Fahrenheit. So in my mind, I know about what 95 feels like. That's like a little bit lower than body temperature, I guess. I can't wrap my mind around how much something in Celsius is. Again, it's because we live in America. But like in Canada, they use Celsius all the time. Like I can't tell you if 16 degrees is hot or cold. It's probably like moderate, I think. I'm not like super confident in that. But anyway, so this is the equation we use to relate Celsius and Fahrenheit. So we're given Fahrenheit and we want Celsius. And then from Celsius, we can easily get to Kelvin. It's not useful to go from Fahrenheit straight to Kelvin, always just go through Celsius in this case. All right, so we are inserting that Fahrenheit temperature. All right, and so divided by 1.8, and that will give us our Celsius temperature. So 95 minus 32, so 63 divided by 1.8. Divided by 1.8. So our Celsius temperature is 35 degrees Celsius. All right. So if we want our Kelvin temperature, that is equal to the Celsius temperature plus 273.15. Okay, and so if 35 is our last sig fig, what should our answer, what place value should our answer go out to? The ones place, because the last common digit that both those numbers have is at the ones place. So 35 plus 273 is 308 Kelvin. All right, so practice those temperature conversions. There you go. All right, so let's keep going. All right, yeah, like I said, talking about states of matter. Okay, so we typically think of gases as being hot, liquids a little bit cooler, solids colder, right? Especially when thinking about water, and the states of matter when it comes to water, like ice, water, or steam. We can also think about states of matter in terms of some of their particulate properties, all right? So we think about the shape and volume of gases, liquids, and solids, but something you might not have thought about is how do those particles move? I know gases, typically are at a higher temperature. We need to boil water in order to get it to turn into steam. So we have to increase the temperature. So those particles in gases like steam are moving much, much faster than liquids or solids. So that's what it's kind of saying here, that the gas particles can go any place in a closed container, that there's a lot of energy within there. Liquids and solids, on the other hand, they don't move as much. Because liquids and solids, we call those the condensed phase, meaning that gravity will take over and they'll take the shape of the container or have a distinct shape. Solids and liquids. The difference is the amount of vibrations and movement. Liquids, they can flow past one another, but they won't go against gravity and go up, right? Solids, on the other hand, they don't flow past one another, but it doesn't mean that solids, the particles, the atoms themselves aren't moving. They are vibrating a little bit. So keep that in mind. And so if we think about, the movement, how close are the particles actually, how close are they to one another? In gas particles, they're far apart. They're very, very far apart. And that kind of tells us a little bit about their density too, right? That the gases had the least density within our charts. Liquids and solids were more dense. And then, within here, liquids and solids, the particles are much, much closer together. So oftentimes their interactions are important. So the idea that we can see a solid, liquid, or gas phase for a specific substance is based upon energy. Kinetic energy and potential energy. So if you've ever taken a physics class, you might have talked about kinetic and potential energy. As chemists, we think about it a little bit differently, all right? But we still kind of use somewhat the same equation. So the big idea here is that kinetic energy is based upon movement of particles, movement, speed, and you'll see this in the equation. Potential energy is based upon the position of your substances, all right? And so really the state that you see of a piece of matter is this balancing act between kinetic energy and potential energy. Potential energy keeping your substance together as a solid, or if you give something enough kinetic energy, that sample, they'll fly off and become a gas. So really what we see is this kind of balancing act. So if we think about our physics definition, kinetic energy versus potential energy, we know that in spot A, this skateboarder has high potential energy, right? But once they start going down the half pipe here, at point B, they'll be going fast, right? They'll have high kinetic energy, but low potential energy because of their position. And then once they get back up to the C spot, they'll have high potential energy again. Again, it's energy based upon their position. Or our friend Katniss here, right, where she has a drawn bow and arrow, how her hands are positioned is giving the bow and the arrow high potential energy based on the position. Because once she lets go of the arrow, what's gonna happen? Or lets go of the string, what's gonna happen? The bow will collapse and the arrow will go forward, right? And the arrow is moving, so that is a example of kinetic energy. So her potential energy, where she is drawing the bow, is transferring to kinetic energy, making the arrow go forward, right? So there's another transfer of kinetic and potential energy. So this is what you should write down. Okay, so just recall, kinetic energy based upon motion. Particle motion, you have to have a piece of matter moving. So if I throw a baseball, that baseball has mass and it has velocity. So we can calculate its kinetic energy. Anything that has mass and is moving, we can calculate potential energy. I keep saying potential, kinetic. We're doing this one, the one on the left first. Mass and velocity. So the note here, in order to use this equation, 1/2 mv squared, mass must be in the unit of kilograms, must be. You can't just put whatever mass unit you want, it needs to be in kilograms. The velocity must be in meters per second, must be. And in doing that, you get an energy value in joules. And I think we'll do a calculation on the next slide. So the big thing here with potential energy, again, based upon position. But as chemists, the general trend is when particles are close together, your sample has low potential energy. The closer the particles are to one another, low, oftentimes negative potential energy. When particles are far away from one another, we typically have higher potential energy. So that's what chemists think about, all right? So again, kinetic energy, particle motion, potential energy, how close are those particles from one another? All right, so if we think about liquids versus gases, in which case are the particles far away from one another? Liquid phase or gas phase? Gas phase. So based upon what I just said, which substance will have the higher potential energy, a liquid or a gas? Gas, because the particles are further apart. Okay, so that's essentially what you need to know when it comes to potential energy, and that's basically it. So let's do one calculation with kinetic energy. We don't have to do this example down here about potential energy. I think the kinetic is more important. So remember, when we use this equation, mass needs to be in kilograms, and velocity must be in meters per second. So that's nice that I give you the velocity in meters per second, but the mass I give you is in grams. So we need to convert that to kilograms. So I know that there are 1,000 grams in a kilogram. So my answer here, mass in kilograms, would be 6.646 times 10 to the negative 21, I think, kilograms. That would be the answer there. I don't even have the answer there. Yeah, so there's my mass. That's the value that I will put into that equation. And then I am given the velocity, 34 meters per second. So I can just put that in there straight into the equation. So in my calculator, we'll go 1/2 mass, so 6.646 times 10 to the negative 21 kilograms times 340 meters per second squared. So 340 squared times 6.646 e to the negative 21 divided by 2 equals the kinetic energy of, what is this? A helium atom is 3.8 times 10 to the negative 16 joules. So joules is the unit that comes out of this energy equation when mass is in kilograms and velocity is in meters per second. I think there's one homework question about kinetic energy. One. So again, don't put any unit that you want in there. It has to be kilograms and meters per second. And then we don't have to do this potential energy one. Okay. So more about joule units and heat and energy. So heat is something that we can observe when it comes to chemical reactions, and it's something, temperature is something that we can measure. So heat is really the transfer of energy from one body to another. What we observe and what we can measure is temperature. All right, so what chemists use to think about energy transfer into substances is specific heat of a substance. So specific heat, I mentioned before, is a intensive property, so it's dependent on the identity of your substance. Identity of your substance. So oftentimes the units that we see for specific heat is joules per gram per degree Celsius or calorie per gram per degree Celsius. So what this means, what this unit means, it's how much heat does it take to raise 1 gram of substance 1 degree Celsius. That's all that means. So joule, remember, is our unit for energy. But calorie is also another way that we can measure energy. So joule, the one that we got with our kinetic energy equation, the relationship between a joule and a calorie is right here, right? So 1 calorie is 4.184 joules. So you might be thinking, oh, calorie like on your Cheerios box. So the nutritional calories, just to make things confusing, nutritional calories are not the same as this calorie. All right, so a nutritional calorie, it's actually with a capital C if you look at the box. Okay, a nutritional calorie, it's with a capital C. So 1 nutritional calorie is actually 1,000 small c calories, just to make it, confusing. And so therefore, therefore 1,000 calories, that will be 4,184 joules, okay? So if you eat 1 calorie, 1 nutritional calorie worth of something like, I don't know, like a piece of celery, then that would be 1 nutritional calorie be 1,000 small c calories that we're using in chemistry here, or about 4,000 joules of worth of energy. So oftentimes we use calories as well, and what that unit is based upon the identity of water and how much heat water absorbs. Yeah. Is it in lowercase? Is it not? Okay, yeah, so that should be a lowercase c, yes. But in the definition that we have here is the lowercase c one. So everything here is the lowercase c, so this should be lowercase. But it's at the beginning of a sentence, so it's hard to get word or like PowerPoint to do this. So this is lowercase. Usually in work, or like a question, I will always say a nutritional calorie with a capital C, just to make it super obvious that I mean like, you know, a big calorie. Actually, if you go to Europe and you look at their boxes, okay, because they're I don't know, they're smarter with units than we are. They don't put calorie with a capital C, they actually put kilocalorie. Because if you look at this, a nutritional calorie is a kilocalorie. Right? Because 1,000 calories are in a nutritional calorie. So if you go to Europe and look at those boxes, they will say kilocalorie. So they're smarter than us. So 1 kilocalorie. Okay, when it comes to units. All right, so calculations with heat and specific heat. So memorize this equation. Q equals MCAT. That's how I memorize it. Q, or heat, energy, equals M, mass, times specific heat, that's your C, times delta T. That means change in temperature of your sample. So I memorize that Q equals MCAT, where the triangle is an A. All right, so here are all the numbers that you input to get a change in temperature of a sample. So here are some specific heats given of substances. Okay, so the question is, how much heat in calories is required to heat 150 grams of water from this temperature to this temperature? All right, so let's just kind of break this down and make sure that we get all these units. We are calculating heat, so this is Q. We want to know what is Q in calories. So we are heating 150 grams of water, so that 150 is mass. Okay, so that's Q equals M. Now we need to do the CAT part. So it gives us this temperature increase. So recall here, delta T. Delta T is always, by convention, your final temperature minus your initial temperature. So if we calculate delta T here, we're going from 15 to 25. What is our final temperature? 25. I don't know what this means. Yeah, 25. That's our final temperature. Our initial is 15. So delta T is 25 minus 15. Okay, I see. So delta T is 10. Specifically, it's positive 10. All right. So what that means is that during the course of this, you know, whatever we're doing here, our temperature of our water went up 10 degrees. It's a positive number. So depending if the temperature went up or down, would change delta T here, but in this case, it's positive. All right, so we have M, we have delta T, we just need the C, the specific heat. So we are heating water. So if we look here, specific heats are typically given to you, okay? And so here, liquid water is 1 calorie per gram degree Celsius. So that is our C value, or specific heat that we're going to use in our equation. So now it is just a process of plug and chug, right? So Q equals M, C, delta T. So if I kind of look at all the values that I have C, I have M, and I have delta T. So mass is 150. CS is 1, and I'll just put the unit here so you can see how the units cancel. And then, so it's 1.00, sorry. And then we have our temperature here, and that is 10 degrees Celsius. And that will give us Q in this case. So if we look at these units, grams cancel, and degrees Celsius cancel. So that gives us just the unit of calorie at the end. And I think if I inspect here, we should have 2 sig figs at the end because it's all multiplication. So if you put that together, so 150 times 1 times 10, the Q, the amount of heat required to raise the temperature of this water by 10 degrees is 1,500 calories with a small c. 1,500 with 2 sig figs. So it should be 1.5 times 10 to the 3 calories. All right, so Q equals MCAT. So we can do another calculation similar. I just give you different parts. So here, I want you to calculate the specific heat of a substance. This time, I want you to calculate this specific heat in joules per gram degree Celsius. So here, I give you a mass. So there's my mass. Here, I'm telling you the metal absorbs 250 or 275 joules, so that's Q. And the temperature rises from 20.2 to 24.4 degrees Celsius. So that will help me calculate delta T. So this is the exact same equation. I just give you different parts of it, and you just have to calculate something else. So if we go through it and see what we're given, I give you Q, I give you mass, I give you delta T. So we are calculating for C, specific heat in this case. It should have a subscript S, sorry. There. Okay, so yeah, it's just plug and chug again. We just need to calculate delta T real quick. So the final temperature is 24.5. The initial temperature is 20.2. This is subtraction. So to what place value does our answer need to go out to? The 10th place, yes. So 24.5 minus 20.2, delta T is 4.3 degrees Celsius. So that actually has 2 sig figs. And so make sure when you plug that into the next step here, you recall that it has 2 sig figs. So Q in this case is 275 joules, mass is 24.8 grams, and delta T we just got is 4.3. Degrees Celsius. So based upon all this, that's all multiplication division, how many sig figs should our answer have? 2, right? Because the sum of them, so energy has 3, mass has 3, but temperature has 2. So we should have 2 sig figs at the end. So 275 divided by 24.8 divided by 4.3. So the specific heat of this metal is 2.6. joules per gram degree Celsius. You might be asking, well, how did you get that unit? Look, of the units here. There's a joule here in the numerator, and a gram in the denominator, and a degree Celsius in the denominator. So that is the unit at the end, and that's the unit for specific heat. Right? So what metal could this be? Let's look at this. Oh, wait, these are in calories. Never mind. I'm not sure what metal this is. I think I just made up a question. Yeah. 1. That's a great question. So let's go back to that question and do the same thing we did with temperature. Okay, so let's look at these 2 temperatures. So to what place value, what's the rightmost place value known in 25 degrees and 15 degrees? The 1's place. So what is the last significant digit in our answer? Don't look at the answer. Just look at these 2 numbers. If they're both known to the 1's place, our answer needs to be known to the 1's place. 1's place. Okay, so in this case, the 1's place when we do the calculation is 0, but that 0 is actually significant. So I should have written 10 dot. Okay, right. So remember, our calculators are stupid. When it just says 10, sometimes we need to think, okay, is that 0 actually significant or not? That's a great, you pointed out a great thing I overlooked. Okay, so let's keep going. Oh, here's a conceptual question. Okay. So we did Q equals MCAT. Do you have a question? Yeah. Oh yeah, you can do that too. That's just the arithmetic to kind of move things around. So what I did is just isolated CS, so then I could just put everything on in one equation. You could put everything in the original equation and just move stuff around to isolate CS. And that's the same thing like by arithmetic. Yeah, yeah. Okay, so this conceptual question, you don't have to calculate anything, okay? So imagine we have a block of copper, 10-gram block of copper, and a 10-gram block of wood. We supply the same amount of heat to both of those blocks. Let's say they're at room temperature initially. Which one will have the higher final temperature? Don't calculate anything. If we have a piece of copper and a piece of wood, which one will end up in a higher temperature? Here, let me phrase the question a little bit differently. Imagine it's 100 degrees outside Fahrenheit. It's really hot out. You have the option to sit on a metal bench or a wooden bench. Which one are you going to sit on? Yeah, see, instant, right? Everyone thought of that instantly. But when I phrase it like this, you're confused, right? Or I don't know, it's not as intuitive. But everyone knows that they want to sit on the wooden bench. So based upon that, which substance has the higher final temperature, the wood or the metal? The metal, or copper in this case. All right, so if you did do a calculation here, you see that wood has a higher specific heat. So like here, it's hardwood, softwood, whatever. Copper has a lower specific heat. Okay, so recall this is calories per gram degree Celsius. So what this means is it requires more energy to raise a gram of wood 1 degree Celsius. So that kind of tells you, when we think about will you sit on a wood bench or a metal bench when it's hot out, tells you that the temperature is going to be lower because it requires more energy to raise the temperature versus like a piece of metal. See, all these metals have low specific heats. It means less energy is required to raise 1 gram of that substance by 1 degree Celsius. And I think we think about that kind of in our everyday life, but these are the numbers that prove it, prove what we are experiencing. Okay, so there we go. So what's the answer here? Is it copper or wood? Copper has the higher final temperature, right? And again, because if I gave you the option, do you want to sit on a wooden bench or a metal bench on a hot day? Everyone chose wood bench. And this is the reason, because metals have lower specific heats, easier for it to heat up in the same environment as if we compared it to wood. Okay, so where are we at now? All right, so we're almost done. So we're in lab, we're measuring matter. So a detail that I want to point out, it's not just significant figures when choosing, how many digits to report in a number. A measurement always has 2 things. It always has the number that you report with significant figures, but it also has a unit involved with it. So always make sure that you have a number and a unit. So here are some examples, right? That if I make a measurement 16.1 centimeters, this has 3 sig figs, right? Again, the number of sig figs depends on the precision or the number of tick marks on your instrument. Or if we have a mass amount, this would have 5 sig figs. Again, the number of sig figs depends on your instrument. So here I would be taking a mass measurement with an analytical balance that goes out to 4 decimal places. Okay, or this measurement, 221 students. So that's how many students are enrolled in this class right now. How many sig figs are in this number? Infinite, yay. See, I tried to trick you. Yeah, this actually has infinite number of sig figs because I didn't estimate this. I straight up went to Buckeye Link, I looked at the number, and that's it. That's an accurate, precise, exact value. So it actually has infinite sig figs. This is a counting number. So it's a little trick. All right, so these 2 are actually measurements that you would take in lab. All right, so when thinking about lab measurements and calculations, we need to think about precision and accuracy. This is a measure of how good a scientist we can be. There's a difference between precision and accuracy. So if we look at these, everyone thinks about darts, dartboards when thinking about precision and accuracy. Precision is your grouping. Accuracy is how close you are to the target value. Okay, so here, accuracy is the degree of reliability of a measurement. So it's how close your measurements, or essentially how close is your average to a true value. So the subtlety here for accuracy is you need to know the true value in order to comment on how accurate you are. So that's the deal here. Precision is different, and I feel like some folks, they use these terms interchangeably oftentimes. Precision, why did I write precision twice? Does anyone know what the word here should be? What? I didn't quite hear what you said, but the answer in this blank should be reproducibility. There might be a better synonym for it, reproducibility. Okay. Consistency is a better word, yes, yes. Consistency, okay? So yeah, if you can make consistent marks in the same place, that is your precision, all right? So it's how close your measurements are to one another, right? Just one another. So it has nothing to do with a true value, but oftentimes people use them interchangeably. So if we look back at this dartboard, we can clearly see that this last one has good accuracy and good precision. This middle one has good precision. See how the grouping's really good, but it's off center, so the accuracy is not good, while this first one doesn't really have good accuracy or precision. Its accuracy is okay, because I guess if we took the average of all of them, they would be kind of in the center. The accuracy would be okay, but the precision is not good, at least compared to the other ones. So let's look at like a real life like measurement. So what did we say here? What was the word you said? Consistency, consistency. I'm not very good at words. Consistency. Got a PhD in chemistry, not spelling or words. Okay, so here's an example. We have two students. Students 1, student 2. They measure something 4 times. All right, and I give you the average of all 4 of those measurements. So the question is, okay, the true value of the mass is 21.3. Here, the crucible and lid actually weigh 21.3. So you need to recognize that this is the true value that I'm giving you. Okay, so the question is which student is more accurate, which one is more precise? So again, accuracy, you take the average and compare it to the true value. So which student is more accurate, 1 or 2? 2, because their average is closer. But then which one is more precise? What we want to do is look at the range of the measurements. So I didn't give you that, so we actually have to inspect them. So look at the low value and look at the high value. So it looks like 21.7, 21.9, that's the high. So the range is like 0.2 for student 1. Student 2, their low is what, 20.1? Ooh, and 22.0. So their range is 1.9. It's almost 2 grams is their range. So you can clearly see who's more precise. Who's more precise, 1 or 2? 1? 1, narrower range. We want to look at the narrow range. Narrow range, okay? If we were in a statistics class, we would say calculate the standard deviation, but that's not necessary. Just look at the range for these measurements. So the question is what if I didn't give you the true value? What if this question, you didn't, I didn't give you this? If I didn't give you this, how would the answers change? So the answer, precision wouldn't change. Student 1 is still more precise, okay, because that's just their grouping. But who is more accurate, we actually wouldn't be able to tell because we don't know who's closer to the true value. So it's oftentimes students they'll mix up precision and accuracy and think they're synonymous, but they're not. Accuracy is always compared to a true value. And if we don't know the true value, we cannot comment on accuracy. Okay, so that's how the question would change. Okay, all right, so let's keep going. All right, so thinking about units and prefixes and kind of putting them all together, I have to note that, the units that we use in this class might not be the same units you use in like a health setting. So recognize that there are a lot of different conversions between empirical units, like quarts, pounds, things like that, to metric units. So these are always things that you can look up when you are in a health setting, and it's very important because oftentimes drug dosing are in metric units, like milligrams per kilogram of body weight. Those are metric units. But when you go and weigh someone on the scale, typically we're weighing them in pounds. So recognize that these prefix conversions between different units is very important. Always be aware of what unit you're working with. So like here are the customary US units, and then the SI or metric units that you'll oftentimes see. So yeah, in health settings, you're really working with a lot of different units. The US, those types of US customary units, and the units that like the doctors and the scientists use, right? So why prefixes matter, right? So reading and interpreting lab results, right? If you ever like gotten blood work done and looked at the results, oftentimes you'll see numbers and they'll put like flags if you're in a bad range, okay? If you've ever done that, gotten like blood work done, yeah. So they're measuring, you know, small quantities of like elements or some type of chemical or protein in your blood and measuring how much you have and comparing it to a reference. Right, so the numbers that you see there, they always report these numbers in a number that you can read pretty easily. So oftentimes they're measured in really weird units, but the reasoning here is it's much easier to read large numbers. So if a normal range of a concentration of something is like between 1 and 10, those types of numbers are really easy to read, like between 1 and 10, versus like 0.0001 and 0.0002. Like those are harder numbers to read. So oftentimes health settings and what you read in lab results, right, you want them in normal ranges, right, that are easy to read. Like all of these numbers are really, really easy to read, but they're in really weird units. But the reasoning for these weird units is so the range is in something that we can read. Okay, so keep that in mind. So, or over here, like milligrams per deciliter, kind of like a weird unit that we have two different prefixes at once, but the reasoning is so the results that we read are in a range that is easy to see. Okay, so another unit that you will commonly see has to do with IVs. Intravenous, blood work and administering medicine through an IV, and that's drop units, okay? So, we have a certain concentration of drug that we want to deliver to a patient. We didn't need to know, okay, how much of the drug is in each drop. We can change the settings on the IV bag to administer a certain number of drops per minute. So here are some calculations that we can do. And really what it is just an exercise in dimensional analysis. So it's can you play with units to get what you want at the end. So oftentimes in IVs, you'll see some weird units here. Drops per milliliter is our drop factor. So GTT. Just to kind of simplify this, GTT, what that means is drop. Okay, GTT means drop. So in this next line, it says drop factor. Okay, it's the number of drops to make up 1 milliliter of solution. So the drop factor oftentimes has this unit, GTT per milliliter. Okay, so what that means here, 20 GTT per milliliter means 20 drops per milliliter. So this means 20 drops per milliliter, right? So that means if we had this certain IV bag and counted how many drops make up a milliliter, it would be 20. So just keep that in mind. So oftentimes it's all about timing. So if a doctor says, I want this amount of this drug administered to this patient over a 12-hour time period, you got to do some calculations to figure out, okay, what is the drop factor of the medicine itself? What is the setting that we need to set the IV bag to make sure that we get enough drug to this patient based upon the doctor's orders. So yeah, calculations with dosage is just an application of dimensional analysis. So here is an IV question. So just remember, GTT means drop. So it takes 10 hours to deliver 1 liter of fluid through an IV with a drop factor of 60 GTT per milliliter. What should the flow rate or drop rate in GTT per minute or drops per minute be set to? So it is asking us, okay, what's the drip rate? So drops per minute. How many drips off the IV bag should we set that to? So we want to know drops per minute. So let's figure out, okay, how many drops are in 1 liter? Because that's how much of the IV that we're delivering. We need to figure out how many drops are in that 1 liter. And here, if we look at the denominator, minutes, so we're given a time, it's 10 hours. So we need to figure out, okay, how many minutes are in there? So if we can do 2 different dimensional analysis setups, divide them by each other, we can get the drip factor. I looked up drop factors and stuff on Google, and they gave like equations But I don't like memorizing equations. So if you, again, can just utilize these units and see where they're coming from, I think you'll be better off here. I mean, you can look up the equations if you want to, but it's really just dimensional analysis here. So we need drops. We need to figure out how many drops are in a liter. All right, so 1 liter. So let's look at some of these values that they gave us. So 60 GTT per milliliter. If we change that to an equality, GTT per milliliter, that means there's 60 drops, or GTT, equal to what? 1 milliliter. So it's the thing that's in the denominator gets that inferred 1. So look, this allows us to go from a volume to number of drops. We're starting with a volume, but unfortunately it's in liters, but that's okay. We know a prefix, right, to help us go from liters to milliliters. How many milliliters are in a liter? 1,000. So 1 liter, 1,000 milliliters. So now I'm in the unit of milliliters. So now I can use this conversion factor, milliliters, to get to drops. So see how 1 milliliter on the bottom, 60 drops. And that equals something. I guess 60,000 drops. So that's what's going to go on my numerator in drip rate. But now I need to figure out minutes here. So we are starting with 10 hours. Okay. So what conversion will I use here? How many minutes are in an hour? 60. So 1 hour equals 60 minutes. So where's the 60 going to go, top or bottom? Top. Because if we put the 60 on the bottom, 1 hour will go on the bottom, 60 will go on top, 1 hour will go on the bottom, and then those 2 units will cancel, and then we get 60 minutes up top. So our time here is 60 minutes. So in order to calculate drip rate, we would just take those 2 values we just calculated, 60,000 over 600. So 60,000 drops over 600 minutes equals something. 1, 2, 3, 600, I think it's 100, yeah. 100 drops per minute. So a little bit more than 1 drop per second off of that IV. All right, so it's just using units. All right, so last thing here, last set of slides. Percents in health. So you'll oftentimes run across percentages in health. So the big thing with percentages is, we're given a percentage, but oftentimes we want to think of that in terms of the fraction. All right, so that means we have to divide the percentage given by 100. So percents are really important because oftentimes active ingredients in drugs are given as a percentage. What's really important is child dosing. So if there's a certain drug and you want to administer it to a child, oftentimes it's a percentage of the adult dose. And that's really important too. And I read something on Facebook and I thought it was really interesting. As an adult, if you are given too much of a drug, you can tell your doctor, like, hey, I'm feeling side effects of this drug, can you lower the dose? Can we come up with a plan? But if you are giving some type of medicine or drug to a child or a toddler or a baby, can they vocalize if there's interactions or they're experiencing too many side effects? No, they can't. So correct dosing for children is very, very important. Oftentimes when a child comes in for a doctor's appointment, and if they're super, super sick, they will make sure and take the time to get a very accurate weight of that child to make sure that they're correctly dosing them to the manufacturer's specifications. Because if they get the dosage wrong, remember, children can't vocalize if something is wrong, right? So dosing for children, very important. And oftentimes it's a percentage of the adult dose here. So I think it's best if we just do some examples, all right? So the whole thing here, percent is a ratio. Right, so if we talk about something that is like 30% by mass of fat, that means if something's 30%, we can make an equality, okay, 30% by mass of fat. If we have 100 grams of some type of food and it's 30% fat by mass, that means 30 grams or 30% of 100 grams is fat. So oftentimes when I think about percentages, I turn them into actual qualities instead to help me with it. So let's look at this example here. So once we have this equality, then we can use the conversion factors to get what we want. So here I just made up a question about bodybuilders and supplement powder. Let's say we have a supplement powder that's 85% protein by weight. Okay, so that percentage, when we turn it into an equality, 85% protein by mass means that if we had 100 grams of the powder, that means 85 grams of it, or 85% of it, would be protein. That's how we kind of deal with percentages, all right? So then this is an equality that we can use. So if we wanted this bodybuilder, they want 25 grams of protein, how much powder do they actually need? So I'm gonna start with 25 grams of protein on the top. Protein, I can spell. All right, and so based upon this conversion that I just came up with, do I wanna put the 85 on the top or the bottom to make the units cancel? If I'm starting with grams of protein, is 85 gonna go on the top or the bottom? Bottom. See how with percentages, oftentimes it's difficult thinking like, oh, I do have to divide by 85 or multiply by 85. And so again, dimensional analysis takes the guesswork out of it. I'm in 25 grams of protein, so I want to put this part, the 85, on the bottom of my dimensional analysis. So that means what goes up top? The 100 of the powder. So this is how much protein powder that this person needs to eat to get 25 grams. So 25 times 100 divided by 85, they need to eat about 29 grams of powder in order to get 25 grams of protein. Okay, so in this case, we divided by the 85 to get that answer. All right, so let's do another one. Okay, so here, a human body is approximately 60% water by mass. All right, so I have that there. So again, let's practice converting percentages into conversion factors. 60% water means that if I had a 100-gram human, how much of that is water? How many grams of that is water? 60. That's what 60% means, H2O. Okay, so if we have a 125-pound human, how many kilograms of water is present? So I'm going to start with 125 kilograms of human. So unfortunately, I'm in grams right now, so I'm going to convert those kilograms to grams. So 1 kilogram, 1,000 grams of human. So this is of human. So the question is, do I want to put the 60 grams up top or on the bottom? We're putting it up top because I want to put the 100 grams of human on the bottom because right now I'm in units of grams of human. All right, so 100 is going on the bottom, human. Don't skip this percentage equality step. Don't ever skip equality steps, okay? So then we put grams of water up top. And then what are we looking for? Kilograms of, oh wait, that's why you're all giggling. This should be pounds. That should be pounds. Not kilograms. So the only thing that changes, so 1 pound on the bottom, 453.6 grams up top. I'm sorry about that. But the rest is still the same. So I'm in grams of humans, 100 grams of human on the bottom, 60 grams of water up top. Now I go to kilograms because it's asking for kilograms of water. So 1,000 grams, 1 kilogram up top of water. Okay, so 250 times 453.6 times 60 divided by 100 divided by 1,000. So this is 34. It's one, they're saying 1 sig fig. So 34 kilograms or 30 kilograms of water in a human, if we're 60% water. Okay, so there's one more example here about M&Ms. Okay, but we really don't have time to do these last couple questions here. So instead, I'm going to end chapter 1 right here. So next week we'll start chapter 2. So that means that chapter 1 homework is due on Sunday. But I will post the answers, my worked out answers to these last couple of problems on our chapter 1 page. Okay, have a good weekend, everybody.